Hi, I'm Zuzana from UCL, and I'm working on the development of methods to measure tissue oxygen saturation with continuous wave near-infrared spectroscopy. So, tissue oxygen saturation is a value which describes the balance of oxygen supply and demand in the brain. We can measure it non-invasively with NIRS and hence get a real-time assessment of brain health. Currently, there are many different methods of measuring tissue oxygen saturation. We can, for example, measure it with time-resolved near-infrared spectroscopy, which will give us very precise results. We are focusing, however, on continuous wave NIRS, which usually gives us less information and it is less precise and less robust. However, the main advantage of it is that it's much cheaper. So what we are trying is to develop new methods of analyzing the signal and testing whether we can actually extract some additional information out of it and sort of increase the quality of the measurement. So the idea is to use two different methods that are currently used in continuous wave near-infrared spectroscopy and merge these into a hybrid approach. So these two methods are spatial resolved spectroscopy, which is broadly used mostly in commercial devices, and it's a method that uses a multi-distance setting. So we have a light source and a detector, and several detectors, which lets us measure a slope of attenuation against distance. And then you can calculate your tissue oxygen saturation from it. So it's a ratio of the concentration of oxy and total hemoglobin. Another method is a sort of broadband method. So the difference between spatial resolved spectroscopy and this is that in spatial resolved spectroscopy we use only a few wavelengths. However, in broadband methods we have a whole wide spectrum available. So in our case we work from 700 to 900 nanometers. That method uses theoretical models of light diffusion and fits them to our data to obtain tissue properties, optical tissue properties. Well, and our idea is to essentially merge these so that we can get more tissue properties, but also have that multi-distance setting as in spatial resolved spectroscopy, because that lets us sort of test, that lets us overcome the issue of different tissue layers in a human skull. So our measurements were taken in a tissue phantom, so it's a two-layer dynamic blood phantom. The benefit of it is that you can dynamically change the oxygenation of the liquid in the phantom. And the method we've started to use is essentially, we do a spatial resolved measurement with multiple detector separations. However, instead of just analyzing the slope, normally we apply a model similar to the one in broadband fitting, and we model a slope and we fit it to our actually measured slope. So this theoretically will let us obtain scattering and absorption properties of tissue from continuous wave broadband data. So the results show now, or what I've got now, is that I have very good results in quantifying deoxyhemoglobin. It's visible here when I compare it to modified Beer-Lambert law results. However, issues arise with fitting for oxyhemoglobin. So you can see that when you compare my oxyhemoglobin to deoxyhemoglobin, they should be the same scale to maintain total hemoglobin. However, there is a huge over-quantification. So that's sort of the main issue we'll be assessing in the future.